Okay, we are in section 1.9 now, and we were introduced to linear transformations in section 1.8, and we learned that when a matrix A multiplies a vector X, of course the number of rows of the matrix A has to match the number of elements of the vector X for the matrix multiplication to be defined. But when A multiplies a vector X, it acts on the vector X, and it's a matrix transformation. Okay, and section 1.9 really just expands on this idea. It just expands on it a little bit. So again, let's look at some of these wonderful examples here. So there is a matrix here in example 1 that they call I sub 2. I sub 2 has columns 1, 0, 0, 1, and we call that matrix I an identity matrix. Whenever you have a square matrix whose diagonal contains ones and all of the other values in the matrix are zeros, that's called a identity matrix. And so in example 1, they have I sub 2, that's an identity matrix. And then E sub 1 is 1, 0. E sub 2 is 0, 1. That would be like I and J in two-dimensional space, but we call those vectors E1 and E2. Now, what we do here is suppose we have a linear transformation that maps from R2 to R3. Hold on here. Let me go down here a little bit. Yeah, suppose we have some transformation, okay, that takes the vector E1 and maps it into the vector 5, 7, 5, the vector with components 5, negative 7, and 2. And then it takes the vector E2 and the transformation maps that vector into the three-dimensional vector with negative 3, 8, and 0. Okay, find a formula with that. Find a formula for the image of an arbitrary value x in R squared. So notice they have not given you the matrix A. Okay, they have not told you what the matrix A is here. They're just giving you two transform vectors, okay, based off of E1 and E2. Well, the key to be able to solving this is understanding that T is a linear transformation. T is a linear transformation. So let's go here to the next page. First, what we have to do is write the vector x in terms of, so an arbitrary vector x in R squared, okay, would have components x1, would have components x1 and x2. And what we want to do is we want to write that vector x in terms of the vectors E1 and E2. So the vector x has components x1 and x2. That can be written as the linear combination of those unit vectors, E1 and E2, that you see in formula or line 1 there. Now, since T is a linear transformation, okay, the transformation of the vector x is equal to what you see. Let me see if I can write that out a little bit. There's a step they left out, but let me go to the whiteboard here and show you that step. Okay, one moment here. So let me clear this. Okay, and all right. So we were told that the vector x was equal to x1 times vector E1, that unit vector, plus x2 times the unit vector E2. And we want to know what the transform vector of x is. Okay, well, the transform vector of x is the transformation of x1 times vector e1 plus x2 times vector e2. But remember, t, they're defining it as a linear transformation. It's a linear transformation. And so it has to follow the properties of a linear transformation given in section 1.8. And one of the properties is that the transformation of a sum is equal to the sum of the transformations. That's one of the properties. Now, another property is when you transform a scalar times a vector, the scalar can be brought out front. Of the transformation. That's the second property. Okay, so this is absolutely true. This is absolutely true. The transformation of the vector x is equal to the linear combination of the transformed unit vectors, where the weights are x1 and x2. Okay, and so now if we go back to the example here from the book, now we understand this step 2 here. And what we can do is we can put in the transform vectors for E1 and E2, and then we end up getting the answer here. So really, this is an exercise in understanding the properties of a linear transformation. And I think it's important to talk about it because, you know, for instance, in your homework, problems can get a little bit abstract, and I think this helps make it more concrete. The examples help us understand the theory. I always believe that the best way to understand theory is to have examples, and the examples are either examples from the book, examples in the homework, examples in your mind. The more examples you have, the better off you're going to be. Now, there is another piece, an important part to this. Okay, another part to this. So Theorem 10 says that, let's say, okay, hold on here. Let's say that you have a transformation that maps vectors in n-dimensional space to m-dimensional space. Okay, well, there has to be then a unique matrix unique matrix A, such that the transformation of the vector x equals A times x. And A would have to be an m by n matrix. Okay, and what would that matrix be? What would that matrix be? Well, in fact, the matrix A can be constructed as a matrix whose column vectors are the transform unit vectors. That's how you would construct that matrix A. Okay, that's how you would do it. So I think it would be helpful to look at a couple of examples. Okay, and let me bring up my examples here. Okay, so one moment here. Let me make sure. Yeah, let's look at my examples. Okay, let me give you a moment to copy this. Hold on. One moment here. That isn't actually the example I want. One moment, class. One moment. Let me. Okay, I'm going to have to do this on the whiteboard, this one. Okay, one moment here. Let me go to the whiteboard. Okay, so section 1.9, let's do an example. Okay, let me change this to 2-point font. Okay, so section 1.9. Okay, matrix, the matrix of a linear transformation. Okay, and I'd really like to see, let me just check one thing, class, one moment here. Just give me one moment. Because I thought it'll be easier if I can find this example in my lessons, and it should be there. Yeah, I found it. Hold on. Let's go back here. There, this is what I want. Yep, that's it. Okay. Take a moment to copy this example down. Okay. So let's see what's going on here. So we want to find the standard matrix of a transformation that reflects points through the line x2 equals x1. Now, x2 equals x1, you're used to something like y equals x. How many remember, like, maybe studying reflections about the x-axis, about the y-axis, maybe about the origin? How many have seen that kind of thing? Maybe in their other math classes, reflections. Well, for instance, a function, if it has an inverse, the inverse function is a reflection about the line y equals x. How many remember that? Like with functions and inverse functions, they're reflections of each other. Yeah, that's an example. That's right. Good, Mikhail. Good, Marcella. Good, David. Well, and what we want to do is we want to have a reflection. We want to have a transformation that reflects points through the line x2 equals x1. Okay, so all right, how would we do this? How would we do this? Now let me see. Mikhail has an answer here. And actually, Mikhail, let me see. That answer is actually correct. Very good. Let me show you how we do this. So I have a very detailed solution here, okay? So what you have to do is you're applying this theorem 10 in the section 1.9, okay, that says to find the standard matrix for the transformation. To find that standard matrix, you have to construct the matrix by making the column vectors of the matrix the transform vectors. So let's take a look at the vector E1. I should say, let me be more clear. The standard matrix of the transformation consists of the matrix whose columns are the transform unit vectors. Okay, that would be transformation of E1 and the transformation of E2. So what I have here is I have a picture. I have a picture up here of the vector E1, and there's the point 1, 0. Well, if you reflect E1, if you reflect it about the line x2 equals x1, you're going to get the point 0, 1. So E1 maps to E2. And the transformation of E1, therefore, is E2. So this is a graphical way that we are constructing this standard matrix. Are there any questions so far? Okay, Mikhail, excellent, excellent. All right, well, let's look at now E2. We want to transform the vector or coordinate E2. E2 is right here at 0, 1, and if you reflect E2 about the line x2 equals x1, you get the E1 vector, 1, 0. So the transformation of E2 is 1, 0. And therefore, transformation of E2 is simply E1. Belen, you can take any arbitrary point. Well, I want to be careful about this. you want to, though the transformation of 2 points should uniquely should lock in the transformation. I want to be a little bit careful here. By theorem 10, okay, I mean, this is maybe not the only way to get the matrix of the transformation, but the easiest way is to go ahead and work with the unit vectors and construct then your matrix of the transformation, the standard matrix for the linear transformation. Just construct it using the 2 transform vectors. Okay, and there's a table we can refer to, actually. I mean, this is how, well, what I'm going to do is I'm going to go to table 1 in section 1.9, but this is the easiest way to do it. This is the easiest way to do it. Belen, are you comfortable with that? Comfortable with so far? Okay, good. Let me see here. Let me just okay, so what I'm going to do is I'm going to go to table 1. I'm going to go to table 1 and show you this this transformation here, this matrix A of this transformation. Are there any questions before I go back to the ebook? Okay, let me go back. Hold on here, let me find it. Here we go. So I mean, it's really cool how they do this. They use a little goldfish here to sort of help you see what's going on. Let me go down a little bit. Let me go down here. This always happens to me. Hold on. Now I don't know where I'm at. Hold on. One moment. Let me see here. There we go. So this is table 1 at the end of section 1.9. And here is the reflection about the line x2 equals x1. Sorry, one moment. Let's get this. Hold on here. Okay, sorry. Just give me one moment here. So you see, if you were to take the coordinates of that goldfish and multiply the coordinates by that matrix, by this matrix here, which is the standard matrix that will map, reflect points through the line x2 equals x1, the goldfish would look like it's turning about that line. Okay. So they have lots of little examples here. If we for instance go to the first one, let's say you wanted to do a reflection through the x1 axis, and look at the point there 1, 0, which I have as vector 1, 0. What does 1, 0 get mapped to? If you reflect through the x1 axis, what would the transformation of the point 1, 0 be, which is on the x1 axis? Well, they have two vectors there. They have vectors. So in the first picture in table 1, they have two vectors. They have a 1, 0 vector and a 0, -1 vector. And you notice in the standard matrix on the right, the columns of that standard matrix are those actual vectors. So what's going on? How are they getting that? Well, if you reflect points about the x1 axis, notice that the coordinate 1, 0 is already on the x1 axis. So the coordinate 1, 0 under the transformation maps to itself, right? So 1, 0 goes to 1, 0. That's why the first column there is at 1, 0. But now the second vector is 0, -1. The second column of that standard matrix for the reflection through the x1 axis is 0, -1. How are they getting that? How are they getting that? What vector are they transforming to get the vector 0, -1? That's right, David, the vector 0, 1. The vector 0, 1. So you see, they always are transforming the unit vectors E1 and E2. And the transform vectors then form the columns of the standard matrix. If we look at the second example, here we have a reflection through the x2 axis, the vertical axis. So in this case, they have a -1, 0. How do they get a -1, 0? What vector are they transforming to get the -1, 0 there? That's right, Cameron. They're transforming the vector. We're on this now. They're transforming the vector 1, 0. That maps to the vector -1, 0 with this particular transformation. The vector 1, 0 reflection about the x2 axis would transform the coordinate 1, 0 to the coordinate -1, 0. And so in the standard matrix on the right, you have -1, 0 as the first column. But what about the unit vector 0, 1? Well, if you're reflecting about the x2 axis, 0, 1 maps to itself. You see how that works? And so the transform vector is 0, 1. That makes the second column. Let's look at a few more here in the time we have. Look here, reflection about the line. Let me just highlight this while I'm at it. This is section 1.9, the table at the end. This is, sorry, table 1. It comes at the end of section 1.9. So look here, you see the reflection about the line x2 equals -x1. That's a line with slope -1. So what vector gets mapped to the vector 0, -1? In the picture, I see two vectors. Okay, so Mikhail, you're right. The 1, 0 gets mapped to 0, -1. So the first column is 0, -1 in the standard matrix to the right. What vector gets mapped to the vector -1, 0? 0, 1, E2 vector. So -1, 0 forms then the second column. So you're mapping the unit vectors E1 and E2, which is like the I and J vectors, and then the transformations, the transformations of those unit vectors form the columns of your standard matrix. Let me go look at another one here. Hold on. Let's look at another one here. Okay, here's one. Horizontal contraction and expansion. Okay, so, all right, you have, let's look at the first, I want to be careful here how I say this. So for this example, horizontal contraction and expansion, let's see, what are they doing to the goldfish here? What are they doing to the goldfish? It looks like the goldfish in the first picture, is the goldfish getting, is it getting thinner or fatter? Thinner. So how do you make the goldfish thinner? Is it the same height, by the way? Is the goldfish the same height? Yeah, so the unit vector 0, 1, E2, doesn't get mapped to that doesn't change at all. But the vector, but what vector gets mapped to the K0 vector. Okay, and what vector got mapped to the K0 vector? Is it E2 or E1? Right, no problem. E1, that's right. So you see, if K is between 0 and 1, then the goldfish, the point 1, 0 got moved to the left. But if you move the point 1, 0 to the right, if you map it to a vector to the right, like you see on the right there, what's happening to the fish on the right? Is it expanding or contracting? It's expanding. So you see K is greater than 1. And so, so this is your standard matrix. So you can see where if you take vectors, which are points that form some figure, and you multiply them by the standard matrix, you transform the figure. You transform the figure. And this is, I mean, you can imagine computer graphics, right? There are matrices involved in producing the computer graphic images, the movements, and so forth. Yeah, so how many think this is pretty cool? How many think this is like really cool, section 1.9? Mikhail's liking it. I know we have some computer science people in here. Okay, do we have anybody else that thinks it's pretty cool? Okay, Jacob says it's poggers. I'm not sure what that means, but I'll take that. David's liking it. Okay, so this is really some key concepts behind section 1.9, and on Wednesday's class we'll talk a little bit more about section 1.9, and then we'll move into chapter 2. Are there any questions before I stop the recording here? Okay, very good.